Okay, so yesterday we talked about how to calculate K and actually more specifically how to set up an expression for K. Now what we need to do is we need to talk about the standard equilibrium expression and how to convert between Kp and Kc, as those are going to come up commonly in the AP curriculum. So the formula that allows us to convert between Kc and Kp is this particular formula right here. And the new thing that we need to remember in this particular case is this delta N, which is change in moles of gas. So in this case, we might be given the Kp, you might be given a Kc. We know R is going to be the ideal gas law constant, which is 0.0821 liters ATM per mole per Kelvin. And change in N, or change in number of moles of a gas, is the relationship between moles of products to moles of reactants, as given here. So an example of a problem that we might come across would be to calculate the Kp if we've been given a Kc and we've been given at a very specific temperature, and we have this equation at equilibrium. So the very, very first thing that we are going to do is we're going to take Kp equals Kc times R T change in N. Now, in this case, we know that the Kc value is 1.67 at 500 Kelvin, and we know the R is 0.0821 liters ATM per mole per Kelvin. Excuse my thumb before. And the change in moles is equal to products minus reactants. And in this case, when I look at the balanced chemical equation, I see that I have it's already balanced as it's written, 1, 1, 1. So what I'm going to do is I'm going to look at my products. So in terms of change of N, my products is 1 mole of gas, and my reactants, I have 2 moles of gas. So the change in N in this case is a -1. So when I set this problem up to calculate Kp, Kp is going to equal Kc, which is 1.67, times R, which is 0.0821 liters ATM per mole per Kelvin, times T, which is 500 K, and that whole thing, let me do it this way. So this whole quantity is raised to the -1. So when we plug this in a calculator, we have to make sure that we take care of the 0.0821 times 500, raise it to the -1, and then multiply it by the 1.67. And so when you plug that in your calculator, we get a value for Kp to be somewhere around 0.047, not 47, 0.0407. Now, in this particular case, we talked about the other day that K doesn't really have a value or a unit, so we're going to leave it as it is. So there's how we convert to Kp from Kc, and I think that you should be able to figure out the rest of those. Is going to be 15.4, 15.5, 15.7, 2.6. So now there is this range of equilibrium constants, and this diagram here, I think, sort of drives home what that range is. So if the K value, the equilibrium constant, is smaller than 10 to the -3, so like 1 times 10 to the -3, so like 0.001 or something, we are living in a situation where the equation is mostly reactants and very little products, so it's not at equilibrium usually. Or it could be at equilibrium, but that's just when the K is very, very small. When the K is very, very large, something bigger than 10 to the 3, so 1,000 or greater, we have a lot more products than we have reactants, and that's in a situation where the mixture of the reactants versus products is heavy product. Somewhere in the middle is somewhere between 10 to the minus 3 and 10 to the third. That's when our reactants and products are in significant amounts. They don't have to be equal, they just have to be in significant amounts. And this should say times 10 to the minus third, and this should say times 10 to the third. So how big K is tells you how far the reaction has actually gone forward. So if K is small, something smaller than times 10 to the third, at equilibrium, the reaction is mostly reactants. This is a little redundant, but it is important to understand. If it's bigger than 10 to the third, it's mostly products, and if it's around 1, it has significant amounts of both reactants and products. The other thing that we have to keep track of is the reaction quotient, which is something we call Q. So we can use the equilibrium constant expression to check to see if the reaction is at equilibrium under a particular set of conditions. When we have equilibrium in a particular reaction, Q is equal to K. So the equilibrium constant and the reaction quotient are the same value. If Q is less than K, there's not enough product, so the reaction will continue in a forward direction until equilibrium is released. That is that we would have a lot of reactant and not enough products. So when Q is more than K, there's way too many products in order for us to be at equilibrium. So the reaction will reverse until we get to equilibrium. And since Q and K are ratios, we know that they're going to be unitless numbers again. Go back here. Now this diagram helps us to illustrate what's going on. When a reaction is at equilibrium, Q and K are equal to one another. And that's kind of the goal of most chemical reactions, is for them to be at equilibrium. If Q is larger than K, that means we have more products and we are moving back towards reactants. If Q is if Q is smaller than K, we have more products and we're moving back towards towards products. So if Q is smaller than K, we are moving towards products, and if Q is bigger than K, we have more reactants. So we talk about shifting to the left and we talk about shifting to the right. So in this particular instance, we're looking at these. If Q is greater than K, we have more reactants forming, and we're going to shift back to the left to get to equilibrium. If we have Q being smaller than K, we have more products forming, and we're going to shift back to the right to get to equilibrium. And we'll see how this works out. Let's see, a minute. Now, here's a diagram of a graph of concentration when Q is not equal to K and when Q is equal to K. And the reaction that we're looking at here is N2O4 is reacting to form NO2. Now, in order to balance this particular equation, which it actually has not balanced, we need to put a coefficient of 2 here. And when we do that, hopefully we'll see that we start with N2O4, right here with an initial concentration, and the initial concentration of NO2 is at 0. And as the reaction proceeds, we eventually get to a point where Q is equal to K. And when Q is equal to K, again, note that the amount of NO2 and the amount of N2O4, reactants and products, are not necessarily equal. They are just at equilibrium. So as reaction goes over time, it's going to stay at this equilibrium. Now, if something stresses the system and we add more product, then if we add more product than equilibrium, then we have to push the reaction into reverse to go back to some of the reactant, and vice versa. So in this problem here, we have N2 plus hydrogen reacting to form ammonia. So the equation is balanced for you, and you're asked to write the expression for QC. So again, just like writing the expression for K, it's going to be a very, very similar situation. So in this case, I'm going to write QC, and QC is equal to concentration of products over reactants, and the products are in this case is the NH3, so I'm going to have concentration of NH3, and that's going to go over the reactant, And then I'm going to put my reactants underneath. So I'm going to have concentration of N2, and I'm going to have concentration of H2. Now, we have a balanced chemical equation, in which case we have a 1, we have a 3, and we have a 2. Now, those we are going to place as exponents, just like we did the last time. So I'm going to put an exponent of 2 next to the NH3. I'm going to put an exponent of 3 next to the H2, and I'm going to put an exponent of 1, which I don't need to, but I'm going to do it here just for sake of argument, next to the N2. So that's our expression for QC. For part B, it says decide whether the system is at equilibrium if there are 0.249 moles of N2, 3.21 times 10 to the minus 2 moles of H2, and 6.42 moles of NH3 in a 3.5 liter flask. So what I'm going to do is I'm going to go ahead and I'm going to calculate the concentration of the NH3, the concentration of the N2, and the concentration of the H2. You can do this separately. I'm going to kind of combine them all into one step because I think it's a little bit easier that way. So in terms of the NH3, to calculate the concentration, we know that molarity, right, is moles over liters. And since we know the molarity and we know the entire volume of the flask, and we're talking about gases, and gases expand to fit the entire container that they're put in, I'm going to write the expression to look something like this. So I'm going to take the 0.249 moles of NH3 over the volume of the flask, which is 3.50 liters, and raise that to the second power. I'm then going to go ahead and do the exact same thing for the N2, which in this case, we know that the amount of N2 is 0.249. Ooh, did I screw that up? Shoot, I did. Darn it. Let me go back and fix this. I made a mistake. It happens. So I'm going to get rid of this value here. And I'm going to put it should be 6.42, sorry. 6.42 moles of NH3 in 3.5 liters. Whew, that makes a little bit more sense. Then I'm going to take the 2.49 or 0.249 moles of N2 over the 3.50 liters and raise that to the first power. And then in terms of H2, I'm going to take 3.21 times 10 to the minus second moles of H2, again, over the 3.50 liters. So when I go ahead and solve for QC, or the reaction quotient, I calculate the concentration. Oops, wait, I got to raise this to the third power. Better not forget about that. So I'm going to raise that to the third power. So when I plug all these values into the calculator, I get a value for QC to be somewhere around 6.12 times 10 to the 7th. Again, there's no unit here. So it's 6.02 times 10 to the 7th. If it was at equilibrium, QC would equal KC. But at this point, we have 6.12 times 10 to the 7, which is significantly larger than KC, which we were given to us in the problem as 1.2. So what this tells me is that we are definitely not at equilibrium, and it tells me that my products are more than my reactants. Jeez, I can spell. So it tells me that I'm shifting towards my reactants in this case. Okay. Another thing that we need to discuss, I thought I might, I'm going to draw yourselves a little smiley face right here, one of these guys. Maybe something like that. No, moving on. I guess I don't, so I carry on. Now, the other thing that we need to remember is that when you work with Q and K in other cases, what ends up happening is you end up with a some exponential math that we have to kind of keep track of. And one of the things that we have to remember is that we talked last unit about multi-step mechanisms. And so if a reaction has multi-steps, the overall Q or the overall K will be equal to the product of K1 of reactant mechanism for 1 or 2 and 3, so Q1 times Q2 times Q3, or K1 times Q2 times K3. Those are things that can happen. There's also things that we need to remember is that sometimes we will take a reaction that's given to us as a mechanism. We might have to write it in the reverse way in order for us to get the actual equation that we're looking for. And we do that when we put the reaction in reverse. What we're really taking is the reciprocal of Q or K of the forward reaction. So if we're given our Q value, we have to take the reciprocal of the forward value. And then there's also coefficient multiplication that occurs, which means that if you multiply all the coefficients by a reaction in a number, you have to take the Q or K to the power of that number. So in this case, if we multiplied the reaction by a value of n, say, when we write the Q, it's products over reactants, and then we raise that to the value that we multiplied the reaction by. So your homework assignment. Here's a reaction that we are going to look at, and it says the following equilibria are attained at 823 Kelvin. We have the Kc value for the first mechanism step, which is 67. We have the Kc value for the secondary mechanism step, which is 490. And it says based on these equilibria, so they are at equilibrium according to that, calculate the equilibrium constant for the following reaction. So when I'm looking at the mechanism, I see that I have COO, so cobalt oxide, and hydrogen reacts to form cobalt and water. I see, which is a product. Water is a product. I see that cobalt oxide and carbon monoxide react to form cobalt and carbon dioxide. And so when I'm looking at those two things, I'm seeing to myself that carbon dioxide is a reactant. So in this case here, what I'm going to end up doing is I'm going to end up having to flip this reaction. And when I flip this reaction, I actually end up with the reaction that I'm trying to obtain. So in reaction step number 1, I'm going to take CO plus H2, and it's at equilibrium to make carbon or cobalt and water. And I have to flip the second reaction so I can get carbon dioxide as a reactant and cobalt as a reactant, and that will give me cobalt oxide, and it will give me carbon monoxide. Okay. So now when I go to smush this reaction together, a couple of things I see. I see that cobalt oxide plus hydrogen plus carbon dioxide plus cobalt at equilibrium will make cobalt plus water plus cobalt oxide and carbon monoxide. Now, there are some things that cancel out. So I see that cobalt oxide cancels out on both sides. I see that cobalt cancels out on both sides. And I'm left with water, which is one of the products I'm trying to find, and cobalt carbon monoxide, which is the product I'm trying to find. I'm left with hydrogen, I'm left with carbon dioxide. So that's good. So in this problem, I have managed to get the right reaction, which is H2 plus CO2 reacts to form water and carbon monoxide, which is the same thing. Now, this problem asked us to calculate the Kc. Now, we just said that Kc is equal to K1 times K2 times dot dot dot. So in this case, we know that the Kc for the first reaction is 67. So I'm going to take Kc is equal to 67 times, now K2 in this case, I had to flip this reaction if you remember, and when I flip this reaction, I need to use the reciprocal of its Kc value. So that tells me that in this case, I'm going to have 1 over 490 for my Kc. So my Kc for the overall reaction in this particular case is going to be roughly 0.14. So what this tells me is it tells me my Kc value. And if we were to go and take this a little bit further and have to calculate the Q value, the reaction quotient, we could decide if the reaction was truly at equilibrium or not. We're going to add 15.26 and 15.28. I thought that this was going to take up a little bit more space, so so your problem is going to be 15.4, 15.5, 15.6, 15.7, 15.22, 15.8, 15.18, and I believe 15.44 is where so that's your homework. Enjoy.